All right. Awesome, awesome, awesome. So, what I have right now, also too, if you know anyone in other classes really quickly and you want to like message them that we just started, that's totally cool. So if you have anybody in Nenya's or Soroka's class that feel free to send them the link. But just want to let everybody know this is the final exam. Just the logistics of it, just so you can see. It's 80 multiple choice questions. It's broken down like this. Oh, hey, Evelyn. Oh, just speaking of that, good to see you. And again, I'm sorry for the reschedule. Things just got a little crazy yesterday. But yeah, the final exam is 80 multiple choice questions. In Mr. Nenya's class, you're going to still do it on that piece of paper where you bubble everything in. I'm going to be doing it on Google Forms like normal. There are, in front of you is the breakdown of that final exam. So it's pretty equal across the board. The bonding stuff, I know you're probably looking at that going like, what is that? And why is there so many? To break that down a little bit better, I'm looking at the final right now. The reason that one gets so big is simply because of like the difference with ionic and covalent bonding and polarity. As you guys know, that's a huge part of the second unit we've been doing, or the second and third unit, how Mr. Nenya's been calling it. So there is a large chunk of it. So just looking, again, I'm looking at, I'm looking at Octet Rule stuff. I'm looking at ionic covalent bonding. I'm looking at polarity. I'm looking at periodic table. I'm looking at crisscross. Yeah, and honestly, it's just a lot of that. A lot of that. The lab that we did on the ionic covalent lab, and that's where it's so large. So honestly, it's a lot of that. So what you know what I'm actually going to do? I'm going to actually call this. It's called bonding on the final. I'm going to kind of call it octet and bonding. I feel like that's maybe a better little area for it. But I just looked at the final exam, and that is kind of what it looks like. Math-wise, this is for me. So Evelyn, this is not you. There are 7 math questions total. These are all, again, in the multiple choice. So I'm going to give you a piece of paper where you can do all your scratch work on it. So I'm going to make this red so it stands out a little bit more. And then I'm going to make this red so it stands out a little bit more. 2 densities, 1 temperature, 1 gas law. That's the box that we did with the pump, which we could totally go over. 2 metric conversions and 1 heat. And the heat is Q equals MC delta T. Hey, Roberta.
Hi.
What's up? What's up? Just so you know, you are looking. Oh, hey, Dee. You get extra credit. You get extra credit. I'm writing you down. Cool. And are you two okay with it recording? Again, I am right now recording for the YouTube video. Is that okay with both of you?
Yep.
Perfect. Evelyn, is that okay too? Just to make sure, because they're going to hear and see everything you post. Cool. And again, feel free to spread the word. Again, this is the final exam. Just so you kind of know the breakdown of kind of what's on it. There are 7 math questions, and they're in the multiple choice. So I'm going to give you a scratch piece of paper. You can do them at your leisure. And then when you get to those questions, you can just plug it in. But again, everything's multiple choice, including the math. And it's density, temperature, gas, 2 conversions, and 1 heat for my class. Evelyn, I do believe your math problems will be a little bit different because I went over an extra math topic. So you might only have 6, just to let you know. But it's going to be close. It's going to be close. But yeah, now that you've kind of seen it, let me know. What can I help you with? Give me a topic. I'm ready to go. Look, I'm so ready to go. Watch this. Ooh, wow. Let me get to the chat. Chat. Nice. Bonding in general, done. Done, 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 done. Okay, we're going to go 515, and we're going to start with ionic versus covalent, okay? Sweet. All right, bonding. So, long story short, bonding can be broken up into many different things. We're going to go through step by step. Okay. So I'm going to pause at those steps so I can, one, get the timestamp down for the video, but two, if you have questions, cut me off. Like, please, if you have a question, put it in the chat, cut me off, whatever you need to do. Okay. This is for you. I'm ahead on my master's assignment a little bit, so I can stay later than 9. But bonding essentially is broken into essentially this. A bond is when you chemically fuse two elements. Okay. You are chemically fusing them. Okay. That's the best way to do it. Hey, Jacob. Okay. So with this, there's really 2 different types. You have ionic and covalent. Those are the 2. Okay. Ionic bonding is very strong. Okay. Covalent bonding is kind of like strong, mid, I would say. It's not weak by any means, but there's just such a, I mean, I think you get the point, right? And the reason ionic bonding is so powerful and so strong is because there is an actual powerful, real magnetic attraction. Positives, negatives together, which is why it is metal plus non-metal. Where covalent, right, is essentially non-metal plus non-metal. And again, this is where you're going to get your positive plus your negative. Evelyn, you probably have heard of cation and anion. And it's incredibly powerful. Incredibly powerful. You know all about these charges completely. Okay. Now, that's a totally different topic, so I'm not going to go into that right now. With the charges, though, I do want to tell you it's exactly what we've been going over. +1, +2, weird, +3, plus or -4, -3, -2, -1, 0, octet rule, right? And yes, I have a periodic table mouse in my house ready to go. I'm built different. Where covalent bonds, right, that's where you get into more of that sharing stuff. Okay, because these guys have the partial negatives and partial positives with polarity, which we're going to get to. Okay, but essentially, this is what it comes down to with bonding. It really does just kind of come down to this. And again, the main takeaway, because of all this, electrons are taken or given away. Again, I'm going to write it because, I mean, you guys have seen it before. That's literally the charges that we talked about with the octet rule, valence electrons, stability. It's the same thing. Same thing. No different. It's using that. And this one, again, is with sharing. And then, of course, as you all know, sharing goes into equal and unequal. And that's kind of a good place to start. So essentially, that's bonding just basically in general. And it really kind of all stems from that. Is that answer the question? Hey, Javier. Oh, hey, Andrea. Getting everybody's name down. Just so everybody knows, it is recording. Again, is that okay? Everyone who just came in, I just want to make sure it is recording. Awesome. Andrea, is it okay still? Awesome. And again, welcome, welcome, welcome. You guys get extra credit. Sweet. Oh, thank you, Jacobs. Thank you, thank you, thank you. So yeah, that's the basic general gist. Okay. From this, let's keep going. Okay, let's keep going. So I'm going to switch slides. Did everybody get what they needed? Can I switch to the another page? Okay. Sweet. Okay. Now I want to show you what this looks like. So what ends up happening is this. Okay. Let's say you have, sodium. Okay. Sodium has one valence electron, where something like chlorine doesn't, right? Chlorine is 7. Now, I think you recognize we're doing Lewis structures right now, which connects with this. And by the way, before I forget to say it, this is a metal and a non-metal. So this is ionic. Okay. So this is not connecting the dots, right? I just want to show you what happens with an ionic. So what ends up happening is you have Na and Cl. Okay. Very, very powerful bond. And I'm actually going to show you that really quickly. I'm just going to pull it up. So I'll make sure I get the chart out for you guys. Perfect. Love it, love it, love it. So what ends up happening is as this works, right, chlorine has a value of 3.0. It's incredibly powerful. Evelyn, I know yours doesn't look like this. This is that chart that was on the Vesper chart with all the electronegativity values. This is what mine looks like. So you've seen this. It just doesn't look colored. Do you kind of recognize like the numbers a little bit? Actually make this bigger for you. I just want to make sure you see what it is. Okay, cool. Awesome. And again, I'll say it again. If you have any other friends that need this, I apologize for moving it. But please, if you have friends who need in on this, like at least send them the link. Like, please, the more the merrier. Evelyn's in Nenya's class, so I appreciate. And what this ends up looking like, Na is 0.9. So we'll talk about that in a few seconds. Hey, Manuel. Thanks for making it out. Emmanuel, is it okay that I'm recording? Because I am. I just want to make sure you know that. And good evening. And what ends up happening after the ionic is the sodium's electrons are going to be taken. Chlorine, as you could tell, is way stronger. Way, 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 way stronger. That electronegativity difference is 2.1. So it's definitely in the ionic range. So we're definitely good there. And this is how ionic bonds work. This is literally what a +1 means and a -1 means. I think that's really, really important to think about because a lot of people have it flipped. A lot of people have it flipped. Okay. -1 means gain 1 electron. +1 means lose 1 electron. I cannot understate this enough because this is something that if you flip, obviously you're going to make multiple mistakes, right? And I just wanted to show you this is a great review of the octet rule, but this is how ionic bonding works. You do not have to draw this by any means on the test. There is no Lewis structure drawings on the final. It's just multiple choice. So we give you some photos, which one's right. So you don't have to worry about that. But this is ionic and this is how it works. Is that okay? Hey, Sophia. And Sophia, is it okay that I'm recording this? Just so you know. Okay, awesome. Thank you, thank you, thank you. Thank you for coming. Ah, double checking something. I'm loading something really quickly for everybody. Are there any questions with ionic? Because that kind of is it, and also touches on the Lewis structures, which I'm about to show you. That's what I'm loading right now. And Sophia, if I remember, you're in Soroka, correct? Perfect. Just so you know, this is the Vesper, sorry, not the Vesper chart. This is the electronegativity chart. Just so you know, this is given to you for the final. So I know mine looks a little different. Yes, it will be posted. Yes. And on YouTube. Yes. Yes, it will be. Yep, I'm going to do that next, but I'm going to do a quick detour. All right, cool. I'm going to save this really quickly. Let's talk about those charges really quickly because this is a good transition because we're there. 1835. Okay, I will go back to this, so don't worry. I want to show you this. And perfect. Okay. So, on the periodic table, I just want to take a quick second to talk about that charge thing. Okay? Because like I said, if you flip the plus and minus, you can imagine that's going to hurt you on the final. Multiple different ways. The way I think of it is this. Okay? It's called the octet rule for a reason. For a reason. So, one of the things to mention, the best group is the noble gases. Done. Those are the best elements on the periodic table. They are stable, they are happy, they don't need to do anything, they are unreactive or safe, inert, all those different words. They're good to go. They don't have to do anything. They don't. And that's a really, really beautiful thing for them. But what does that mean for everything else that you can see right now that's black? All those elements that are black right now on the screen are not happy. When they become charged, positive or negative, they're not stable. They do not have their 8 outside electrons. Overall, that causes issues. Okay. And yes, there's exceptions. Okay. I know Mr. Nenya has gone into detail about boron, and boron's weird. Okay. I know that. I know, Evelyn, you probably have heard him talk about boron being an exception. Sophia, I don't know 100% what Mr. Soroka has said about boron. It's okay, though. Long story short, these have 1 valence electron, 2 valence electrons. Welcome back. These are weird. Okay, all of these are weird. Okay, they differ. They could be +1 or +2 or +3 or +4 or +5, +6. When I was in college, vanadium right here, vanadium can be +1, +2, +3, +4, +5, or +6. And it doesn't take much to change them. So it's super all over the place. There is no way that you can tell any of these goofy ones. Okay? The only 3 that you kind of can be safe on is zinc, cadmium, and silver. These 3 in this little Tetris piece right here. Do you need to know that? Absolutely not. You're good to go. But just so you know, these are random. They're weird. Don't worry about it. So we continue the pattern. 3 valence electrons, 4 valence electrons, 5 valence electrons, 6 valence electrons, 7 valence electrons, octet 8 valence electrons, which you can imagine is very, very useful. And that's kind of what it comes down to. Now, with the charges, +1, +2, +3, plus or -4, -3, -2, -1, 0. Okay? Which you can imagine is very, very helpful. And here's the big deal. Okay, let's say we pick nitrogen. Okay, let's say we pick nitrogen. Nitrogen is -3. Okay, and a matter of fact, I'm going to try something really quickly. Let's see how this might not work well. Okay, we're going to try this. I'm going to stop sharing. We're going to go back to the slides. We're going to see if this works. Okay, sweet. I think we did it. Okay, and I'm going to do a new timestamp for this. 23 flat charges. Okay, here's the deal. Everything wants to do this. These are good. So let's say that we have nitrogen. Okay, let's say that we're right here. Okay, which is -3. If you actually go -3, do it. Actually go -3. 1, 2, 3. If you literally go -3 and you go that way, you will notice that this is not good. BE isn't stable, y'all. That's not good. That doesn't have the octet rule. The best thing are these purple ones, the noble gases. You went backwards. You went further away. That can't be right if you think about it. That's making it worse. So it's flipped. So if you ever accidentally go the wrong way, just double check. N-3 is BE. No. Try the other way. Okay? 1, 2, 3. That is good. That is good. This checks out. Because 7 to 10, 10 is a noble gas. So if you ever goof your charges, double check. If it doesn't end up in this area, you're wrong. It's that simple. That's the importance of those charges. So yes, negative means, gain. Positive means lose. And it's all because electrons are negative, you know? And it's really just that. If I hand you a negative, you're negative. If I hand you a card that says -1 on it, you are -1. You drop. And the same thing works if you're positive, right? Let's say that you're SR. Okay, let's say that you're SR. Just to do a positive one. You know what I mean? Let's say you're over here at SR, strontium. Strontium's +2. If you go +2, you end up over here in the middle of the weird area. That's no good. That's not stable. That's in the weird area. You're not going to know about zirconium. But if you go backwards, 38, 37, and I'm just going to draw a little arrow kind of this way for backwards. If you go backwards to 36, 36 is good. So it also works with the positives. And you're probably wondering why I went on a tangent for 10 minutes about this. It's because it's going to be used, right? With polarity, it comes back. With bonding, it comes back. With stability, it comes back. With Octet Rule, it comes back. With Lewis structures, it comes back. Okay? With charges, in general, it comes back. Proton, neutron, electron stuff, right? So this idea that it's flipped comes up half the semester so far we've been talking about it. So I just want to make sure everyone's good with that. I know I rambled. How are you feeling? Is that okay? Does that help? Because I don't want you flipping that. I don't want you flipping that. And I want you to check. I want you to have a way to check. Because if you can check, you got this. It's an 80. Oh, I should go back to it. Just so everyone can see. I'm going to switch. Oh, hey, Anthony. Anthony, that's like literally perfect timing. Anthony, just so you know, I am recording, okay? I just want everyone to see again because I know some people. This is the final exam. So it's 80 multiple choice questions. It's broken up pretty evenly. The reason the bonding is so large is because ionic versus covalent, which we started talking about, octet rule, the charges, polarity, all that comes in with bonding. So that's why this is huge at 26. So just so you know, like if you think about it, this 26 actually makes some sense. And then there are, for my class, my students, there's 7 math questions. I think Soroka and Nenya, I think you're at 6. I went over an extra math topic. You guys didn't. It's small, like no worries. But there's 2 densities, 1 temperature, 1 gas law, 2 metric conversions, and a heat. Okay? The conversions are given to you. But just so everyone knows, that's roughly the final exam. I have no problem telling you that. So it's pretty evenly spaced, as you can see. All right, cool. Are we okay on all that? Is there any questions about like the valence electrons or charges? I do want to talk about covalent next. Are we okay? All right, cool. So again, this was kind of the ionic stuff. Okay. And we just talked about, again, the charges. I'm going to copy and paste this really quickly. And we're going to talk about covalent now. So let's talk about covalent. Cool. So Covalent is the sharing, right? Covalent is going to be your sharing. This is going to be, again, non-metal plus non-metal. It's sharing electrons. I can't type. There we go. It's crazy during the pandemic how I got really good at typing. It like you would be surprised how quick we all got at that. Perfect. We're gonna go perfect. So what ends up coming up with this is, of course, the polarity, right? And the sharing. That's the big thing, right? Because when you have sharing, right, you have two ways. You have equal and unequal. So if it is equal sharing, this is called nonpolar. If it is unequal, it's called polar. And you've seen this come up in a variety of different ways, right? This could also come up with the shape or molecular geometries, okay? Or the bonds. I'm going to make this smaller. I normally call it shape polarity. I know Mr. Name, Mr. Soroka probably said molecular polarity a little bit more. That it's the same thing. It's looking at the Lewis structure, what's going on with the electrons. Okay. And again, this is all about the electrons. Okay. And here's where it comes in. The big thing about this is the Lewis structures in the bonds. Okay. Is the Lewis structure in the bonds. So I'm going to write this down with Lewis. Okay. And I just need to copy and paste this really quickly. Please forgive me. Oh, shoot. I did not copy and paste this whole thing. Okay. We're going to hope all right. And please forgive me. I hope we can get this to work. Oh, that's pretty good. All right. We got that to work. Not bad. Okay. I want to just really quickly go over the Lewis structures. Pardon me for this. Sorry about that. But with the Lewis structures, this is where the dots come in. Okay. Again, it's literally the valence electrons. The dots are the electrons, and it's from the valence electrons. So it's literally 1, 2, weird, 3, 4, 5, 6, 7, 8. Again, 1, 2, weird, 3, 4, 5, 6, 7, 8. Again, we talked about 8 being really, really good. Check it out. There's no empty space. 2, 2, 2, 2. 2, 2, 2, 2. There's nowhere else to go. Octet rule, right? They're stable. They're good to go. There's no other space for anything to go. It's all paired up. Because as you guys know, electron pairs are good, right? No cheating. Don't break up the pairs. They are stable. They're good. Yes, we'll talk about cheating second semester. Okay, fourth, early unit 4. Okay, or 5, depending on how your teacher counts. So this is where they all come from. And again, you got to go in a circle. That's why I have this north, south, east, west here. My students in my non-honors class, like they did really, really well with Lewis. Really well with Lewis. Okay. And the reason they did well is they're not doing stuff like this. That's wrong. right? You're not going to pair up right away. Electrons are all negative. They repel. They're not going to want to be that close together, right? They're single and they're ready to mingle. And again, I know this shifted a little bit, but it's exactly like this. This is correct. And now you can connect and make those bonds. This is good. This is not. And that's really what it comes down to with Lewis structures. To save some time, going back to this, and I'm going to talk about polarity. Perfect. It's kind of like this. If you have something nonpolar, I'm going to really quickly look up a Lewis structure for CH4. That is probably the most famous nonpolar one that we have. I'm just going to copy and paste this image right here. That is nonpolar. HHHH. So that's cool. And I'm going to do H3F. Let's find that Lewis structure. Let's look at this. That is, not symmetrical. That F is not the same. HHH, F. So polarity-wise, this is definitely unequal. This is not symmetric. That is a polar bond for sure. Whereas these are nonpolar bonds. And again, the reason I know that is because the range is 0 to 0.4, and this one essentially is 0.5 to 1.7. Sophia, specifically talking to you, I know Mr. Nenny and I do things a little differently with the number ranges. I don't know what Mr. Soroka does. Does that make sense with the 0.4 and the 0.5? Because I teach point. Okay, perfect. Okay, good. Okay, for my students, this is good too. This is kind of, I know I've been saying 0.4 is the border. It is. Mr. Nenia just teaches 0.5. So for my students, does this remember the number range? The 0.4 is kind of important. I got one yes. Everybody else? Okay, good. Thank you. Okay, there we go. Okay. Okay, better. Sweet. So that's really the key. And again, you are going to have these numbers. This is given to you. Do not worry. Okay. Do not worry. If you know the 0.4 is the border, you're fine. Okay. You're fine. And again, this is given to you. And again, what a great reminder with these three specifically, right? With hydrogen bonding, what a great way to remember. So that is definitely given to you. Supposedly the blue ones, my extra ones are coming in this week. We'll see. But if not, if you need one, I got you. I got you. And that's really kind of it. I mean, honestly, the only other thing I could really show is if I maybe just draw these lines for the symmetry, but I think that's it with polarity. That kind of explains your thought. That's kind of your question. I know that was a lot for one question, but I mean, it is 26 questions. It's over 25% of the final. So did that answer did that answer your question? Awesome. Awesome. So we kind of just, and again, I'm not saying we did it perfectly, and you could totally ask more questions about it, but we kind of just did this. We kind of just took care of this. So what else can I help with? And we can talk more about it. If anyone wants to talk more about it, ask. Like, we could totally go back. I know some people came in a few seconds late as well. So we kind of just did that. Spicy still. Partial and formal charges. Yes, we could definitely do that. Let me write that down. Yes. Let's do it. This is a great question because it's not as bad as it seems. Excellent. Excellent. Okay. Here's what it comes down to. Ha. Ha. All right. Let me make this a little bit bigger. Okay. So here's kind of what it comes down to with the partial charges. I'm actually going to change this to 42 flat. Pardon me. It comes down to this. Ionic charges or formal charges are the exact same thing we just talked about. It is literally the +1, +2, +3, +4, and then forgive me. And then I'm going to, again, forgive me, this isn't going to line up very nice. Oh, maybe it will. Okay, forgive me. Let's see how we do. And again, I know this might be really small for you guys. I'm sorry. I'm going to just put a little baby -4 right here. Okay, I know that's not perfect. Can you guys see that okay? Is that big enough? Not too bad? Is that okay? Okay, cool. So that is literally what we've been talking about. So those are the formal charges. Like, it's literally what we just talked about. It's plus means lose electrons, negative means and negative means gain electrons. So it's literally the same thing we kind of just discussed. There is no difference. For example, like oxygen. What is oxygen's charge? -2. What does that mean? Oxygen wants to gain 2 electrons and go 6 to 8. Why would oxygen lose 6 if it could gain 2? Kind of going back to that whole idea that we talked about, right? So that's a formal charge. So again, these are weird. Just to like say it, these are weird. We don't know these. So no different there. Hey, Danielle. It's recording, just so you know. So that's literally the formal charges. Whereas partial charges, switching gears, those are from polar covalent. So what these tell you is who's winning. That's really what it's telling you. Because if polar, again, is unequal, which means those electrons in between, right, those bonds, the electrons are not in the middle. One of the two elements is strong enough to pull them closer. So it's either I'm getting pulled, I'm getting pulled, I'm getting pulled, or I'm doing the pulling. So, for example, and I think you've seen me do it in class, right? If I'm shaking someone's hand and I'm getting dragged, they're stronger. But if I'm pulling them, I'm stronger. So the partial charges tell you who's the stronger one. And electrons are negative. So the partial negative is stronger. So the electrons are by it. And this one is weaker. And I'm going to add pulled away for this. I think that might be a good way to say it. And those numbers are literally from the chart. So all you would need to do is look at the chart, see which element is stronger. I don't expect you to know which elements are stronger, right? These are the electronegativity values. This tells you that. And yes, I know you probably have figured out F is really strong, O is really strong, and N is really strong because of hydrogen bonds. Okay, you know those three. But I'm not going to make you know, like, phosphorus versus silicon or phosphorus versus carbon. Like, those are common questions. I'm not going to make you make that decision. So you can use this chart to figure these out. And that's really it. You're just telling me who's stronger. And that's it. Does that answer the question? That's honestly it. Sweet. And again, given to you on the test, given to you on the test. Yes. And then Evelyn, I know Mr. Nenya doesn't give you the charges on the periodic table, correct? Because you have the blank one. Is that true? And then Sophia, does Soroka give you these numbers on the top, or do you have to know them? Okay. Awesome. And Evelyn, you have a blank. You're given a blank table, right? I'm pretty sure. So Evelyn, if you're there, just make sure you know this. But I think you can see the pattern. And yeah, that's polarity. That's the charges and stuff. Yeah. What's next? Give me another topic. Give me another topic. I'm ready to go. Yes, you're next. What's up? What can I do? You get red. Excellent. So when you have the polarity, you're 100% right because it's going to come down to shape or bonds. Honestly, if you're talking about the whole molecule overall, there's so many ins and outs that once you keep going with this and like AP chemistry with Mr. Nenya or college, there's so many little ins and outs that it changes. For the final, it's going to be very clear to you what the question is asking. Is it going to be shape or bonds? It's not going to ask you both at the same time. So it won't ask you overall. It's going to say shape, answer, bond, answer, just like the test was. That's a good question. That's a really good question. Oh, no problem. Because honestly, like if you like there's little exceptions with like Vesper and stuff that changes it. If you want to know a little bit more, I can talk to you one-on-one about that. But we're treating this very much like this is an overarching, really good way to look at it. Once you go on to like AP Chem, for those of you that want to, you'll talk a little more specific. But it's very similar. Very, very, very similar. Oh, and Daniela, let me show you the final. I'm going to color that. So we're kind of there now. And again, the math questions are over here. The math questions are all in the multiple choice. So the whole thing is multiple choice. Even the math. You'll get a scratch piece of paper. What can I do next? IMFs, you got it. Excellent, 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 excellent. Okay. IMFs. Yeah, blue has been covered. And again, this is just session 1. So but again, please, just because it's blue, if you have another question, ask. Okay? So, like, don't feel like we're locked out. You can totally go back and ask. So please, please, please do not worry about that. Okay, let me just get this set up. Yeah, let's do IMFs. Because 9 is a good chunk of questions. IMFs. The joke at North Central when I was so I didn't take the first year college chemistry classes at North Central. I tested out because of my AP scores and my physics scores. The joke though, because I tutored that class all 4 years, well, 3.5 years. I tutored that class at North Central. The joke was that IMFs is the entire course. That's how important IMFs are in the big scheme of things. So if any of you are thinking science moving forward in any capacity, because you'll probably have to take a bunch, like for example, if you're thinking doctorate, you need physics. You are going to take physics. IMFs come up a lot. AP Bio. If you're thinking about AP Bio, which I know some of you are actually, the first 2-3 weeks of AP Bio is IMFs. You should have, if you probably didn't realize what was going on, but yeah, there were so many students coming back and asking about IMFs, which of course you can do as well. But just so you know, that's how big this topic is, which is really kind of cool. So IMFs, okay, IMFs. IMFs are between things. They are between things. Okay. So what I'm going to do, I'm going to take some of this, right? And we're going to go perfect. I'm going to use a squiggle as the IMFs. Okay. I know my students are used to that. Sophia, I know that might be new for you. He might do dashes. Or Evelyn, does he use dashes? So like show IMFs in between things? Or oh, hey Christian. Not really? Okay. Sophia, what does he do? Soroka for IMFs. Is it like a dash? Is it a zigzag? Is it a different color? Dash? Okay. I'll do it both ways then. So what it comes down to, okay, and I'm gonna just do this twice just to make it nice. IMFs are the between. Please forgive my very bad dash, but this is the IMFs. It's not these. These are not the IMFs. Okay, these are bonds. These are not hydrogen bonds. Okay, which we'll talk about. Right. It's not that, y'all. It's the between. It's the difference between this is a solid and this is probably I'm going to say this is a liquid. Liquid-ish. Okay? That's what it's between. And again, if you think about all that stuff from Unit 1 with phase change, right? That whole idea that like melting takes energy, freezing loses energy. It's this. During that ice melt lab that we did, right? When you guys took the temperature every single minute, it's this. It's this. And I mentioned that we're going to do that lab again. I wanted to do it here. It just, we ran out a little bit of time, which is totally fine next year, right? But it's this in between. It has nothing to do with the bonds. So I just want to start there. Okay. Nothing to do with the bonds. Now, let's go into like more detail on that. So with IMFs, okay, there are 3 types. Okay. London dispersion, dipole-dipole, and hydrogen bonding. I'm going to shrink this. Let's try 24. Excellent. Okay. And it's important to know what these 3 things are. First off, weak, strong, and very strong. Okay. These 2 go together. Okay. Evelyn, this is definitely more for you because I know Mr. Nenya teaches these 2 slightly differently than me. My students, you can kind of ignore what I'm about to say. So Evelyn and Yerk, oh boy. Evelyn, I know he teaches that if you have hydrogen bonding, you don't have to say dipole. I like saying all 3. So I know for you, it's London and dipole or London and hydrogen bonding. I know that. So just keep that in mind. But these are essentially the same. A hydrogen bond is a very strong dipole. My students, don't worry about it. Same old, same old. Okay? But it doesn't hurt to know that. So, London dispersion is from electrons. This is from polarity, particularly polar. Dipole, polar. And this is from, I'm going to get the notes really quick because then I can just screenshot it, which we like. And again, a hydrogen bond is not a bond. A hydrogen bond is not a bond. A hydrogen bond is not a bond. A hydrogen, I should just make a whole song. That's the last thing you guys need is me singing. So, right, Hunt? Am I a good singer? Don't lie to the children. My wife just lied to you. Oh my word. My wife disrespectful. She just lied to you all. That's crazy. She's really out here. All right, I'm going to. All right, let's check this out. All right, all right, all right. Boop. Nice. We like that. We like that. Excellent. Excellent, excellent, excellent. We like that. We like that. If you have a hydrogen bond, again, it's not those bonds, right? The hydrogen bonds are going to come from, and I'm going to try to find my avatar drawings. I think that's a good way to show it. Perfect. Let me just get my avatar going. Sweet. Found the avatar photo. Perfect. We like that. We like that. We like that. We'll talk about that next. Sweet. So again, it's not the bonds, right? Just going back to that drawing I just did, it's not the bonds, okay? The hydrogen bonds come from the fact that you can have a hydrogen on, like, let's say A, and then you have like a B or something new. It's not these. It's the fact that they're in between each other. So it's like my fist with my fist. This is the hydrogen bond. It's not this. It's this. Strong, weak. It's not this. It's not that. It's the solid, liquid, gas thing. And that's really what it comes down to. With dipole, it's just from polarity. If you have a partial charge, that's the attraction. So it's partial negative versus partial positive. And again, please forgive my symbols. And again, this is from electrons. So again, everything has this. And that's kind of the three. Andrea, does that answer the question? It was Andrea, right? Yes. Andrea, did that answer that so far? We're going to do some examples next. We're going to do some examples. Awesome. Okay, let's do some examples. I'm going to get to test. I'm going to give my test questions. Okay, so Evelyn and Sophia, this is not going to look familiar. Just to warn you. For half of you, this will. Actually, you know what? I'm going to, just in case anyone wants to retake the test, that's not a good idea. Let me find one of my old homeworks with IMFs, and I'm going to take some of the drawings, okay? Of course, I clicked that one. Why did I click that one? That one's crazy. Oh, here, we'll just do these. Here, we'll do all these. I got 6 good examples. We'll do these 6. Pardon me. Sorry, I got a lot of pages open, so I apologize if I am coming off unorganized. It's just a lot of open. Okay, we could do all these. Well, we could do all those. Okay. So, examples. 6340. Okay. And then, okay, I'm going to flip this over. Okay. So you need the Lewis structures. Okay. So one of the things to think about, I got these 6 example problems. Let me do the drawings. Okay. Nitrogen. And again, please forgive anything because of my handwriting right now. There's the nitrogen. This, is that big enough? Are these big enough? Here, is that better? It's probably as big as I can go. Let me try to go a little bigger. Is that okay? Can we see everything okay? Okay, awesome. Okay, thank you. Okay, this one, we don't really need to do the Lewis. I think you could tell what's going on here. Even though the formula is huge, this is what, 1, 2, 3, 4, 5, 6. This is hexanol. So we can definitely figure this out. We have this Lewis structure. Ooh, SCl2. You guys have done that one a bunch. And again, please forgive my very unequal, not good looking dots, but I think you guys get the picture. There's your double dots. Glass is SiO2. Oh, that's terrible. That's not going to work. Oh, I got to put that over here. Ooh. This is sand or glass. And again, please forgive me again on these very sloppy drawings. Okay, so we're good there, we're good there, and we're good here. Okay, cool. Okay, now I'm going to do IMFs in red. Sweet. Okay, we're going to go IMFs in red. Let's go red, red, red. Okay, so how do we tell? How do we tell? What's going on, right? So first and foremost, everything is London dispersion. LD, 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 and LD. Okay. Now, what happens if you have a tie? Okay. What happens if you have a tie? Ties go to more hydrogen bonding. Okay. And I'm going to actually make a timestamp for this. IMF ties, because it matters. What ends up happening is this. If you have hydrogen bonding, you're strong, right? That is a strong connection. But 2 hydrogen bonds beats 1. You know what I mean? Like, that's why water is so powerful. Water has 2 hydrogen bonding sites. 2. That's part of the reason why water is such an incredible chemical on this planet. Like, name a chemical more important than water. Good luck, right? Maybe oxygen, maybe CO2. But I mean, water, you can make a really good argument. With London dispersion, though, bigger ones, such as this one, right? That's a way you can break a tie. So bigger things have more London dispersion because there's more electrons. If there's more electrons, there's going to be more of that little negative force. And again, it moves around, right? Electrons move. And that's really what it comes from. So, for example, like this has more London dispersion than this, and this. I mean, these are arguably close. This one's not as big as this. Actually, is it? That's 6. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, this one's bigger. Yeah, so these are the 2 biggest ones. This big thing and this big thing. This is probably 3rd. Again, are you gonna have to do crazy stuff like this for the final? No, you are not. Okay. But if you could do these, you could do anything. You know. So let's look at the polar ones. That's nonpolar. So that doesn't count. This is an equal. I mean, that has OH, that doesn't. So this one has dipole. This one, no dipole. So nope. Oh, this one's polar. Right? Cl dots, Cl, that's not the same. This is nonpolar. This is polar. That's all over the place. And we're there. And that's kind of where we're at. Okay. Now, with hydrogen bonding. Okay. Again, hydrogen bonding is not a bond. Okay. Hydrogen bonding is between things. So here's a bunch of the water I was telling you about. Okay. So this is all water. This oxygen is stronger, partially negative. Hydrogen is partially positive. This is the IMF. It's this attraction that's happening. It's this negative and this positive being close together. And again, I'm not going to do all of them. You can imagine there's a lot. And I can do this. Oops. That's the hydrogen bonding. So because there's an OH bond, that allows for there to be hydrogen bonding, which is in between. That's important. So that's why when we're looking for these things, right, we're looking for these strong ones, right? We're looking for these connections. NOF, which is NOF, no F, or FON. Right? Chemistry is fun. Right? And again, the reason why you know it's these three, and I've alluded to it a little bit so far today, it's the chart. It's the chart. They're the strongest ones. And hydrogen bonding is the strongest. And it's because these are the strongest electronegative speaking, or like you could think of it magnetically. These are the strongest ones. They're not going to let go. They want things like this. They want things really close. So it's going to be these three right here. Another way to remember 7, 8, 9. So again, if you don't have it memorized yet, because admittedly you do need to have it memorized, just look at the chart. Hydrogen bonds are strong. These are the strongest. Just watch out for Cl. It's not Cl. No Cl. Okay? So just watch these three. So if you forget, just look at the chart. It's on there. Okay, we're not trying to fool you. And actually getting it from the chart is really good. So that's pretty cool. So if we go back to this, we're looking for HO, HN, and HF. So this one has it. This one does not. This one doesn't. This one doesn't. This one doesn't. This one does. I see it right there. There's a site. Here's a site. This one here's the site. So this one also has hydrogen bonds. And again, I'm just going to put ×2 on this one, and I'm going to put ×1 on here, just so you can see that this one's the strongest. And this one's the weakest. It's the smallest. This one's the smallest. So this one's way bigger. Oh, that one's also dipole. That's not symmetric. I apologize. I missed that. And Andrea, that's the other half of the IMFs. Did that help? Did that help, Andrea? Awesome. No, great question. And again, the strongest and weakest correlate to boiling point and vapor pressure stuff, kind of like the labs and demos we did. And yeah, that's IMFs done. Nice. What can we do next? Gases. Yep. All right. Absolutely. I'm going right into it. I just have to find it. Ta-da! It's everybody's favorite. So, gas laws. Okay. Essentially, when we're talking about gas laws, which and we're going to also go to the slides, so don't worry about that. Okay. I just want to quickly show the gas law PFET box. Okay. Now, Evelyn, I don't think you've seen this. Sophia, I don't think you've seen this. You might have. but this explains everything that you need to know with gases. Okay. With gases, okay, essentially comes down to three different things: volume, temperature, pressure. Okay. Volume, temperature, and pressure. And there are gas law equations that follow along with that. Evelyn, that's what you're referring to when you say Boyles and Charles. Evelyn, just to make sure, are you good with Gay-Lussac then? Because there's the third one. Okay, so all three? Got it. Okay, cool. So essentially, here's what happens. Okay. And again, I'm going to show you mathematically too. Okay. But first, let's just think about it conceptually. So no math. No math. Here's our gases. Okay. This is the volume. I can make the volume bigger. I can make it smaller. And anything in between, right? So that works out. I can increase or decrease the gas. This is a big topic second semester. Okay, it's called moles. Okay, my students I know have heard me say that before. We did mole day. So I know it's been a while since we've mentioned that. That's totally fine. Evelyn, Sophia, this is a huge topic second semester. Huge. Okay. But long story short, it means amount. So this is a lot of moles. That's a lot of moles. That's a little moles. And the reason I'm mentioning that is because you're about to notice we're not going to really mess with those. So second semester we will, because the amount of gas matters. You know what I mean? Like if you have a balloon and you have 2 breaths of air in a balloon versus 5, that's a different balloon. You know? Yeah. You know, a hot air balloon with a lot of gas versus a little gas. That's a different situation. So it does matter how much you have, but that's going to be later. So here's what the gas laws kind of are. 1, if I squeeze it, okay, and I'm going to keep this locked in, okay, you can't change the temperature. It's going to stay at 300. If I squeeze this, the pressure is going to go up. If I squeeze something, the pressure is going to go up. So when I let go of this, it's not going to be 12. It's going to be about 24. And I promise you it's going to be around 24. Watch this. How did I do that? Okay. Watch this. This is going to be 6-ish. Not 6-ish. 9? 9-ish? 8.5 to 9. Okay, a little off on that one. Just a little off on that one. How am I so close? Right? It's because of this. With Boyle's law, okay? Boyle's is V and P. Charles is V and T. And Gay-Lussac is P and T. Okay? So first off, Evelyn, that's kind of how that works with that. And it's exactly like you think. If you squeeze a ball, the pressure goes up, but the size goes down. That is inversely related. Let me prove that to you again. If I lower the volume, if I squeeze the ball, the pressure inside that ball is going to go up. And you see it just did. No difference. If with Charles, if you have a hot air balloon, if I heat up the gas, the temperature is going to go up and the balloon's going to get bigger. If I cool it down, it's going to shrink and get smaller. No different than you taking a soccer ball or a volleyball or a football or a basketball or a kickball or whatever, dodgeball, whatever you have in your house that's a ball right now, throw it outside tonight. Look at it in the morning. It's going to look deflated. Look at bike tires outside. Look at car tires outside in the winter. They look shrunk. Well, if the temperature is down, the particles aren't going to move as much, right? Remember, temperature is speed. Remember that. Temperature is not hot and cold. Okay? Temp is fast and slow. Okay? Heat is hot and cold, right? Cold doesn't exist. Cold's not a thing. Cold's not a real thing. But that's what it comes down to. And with the last one, right, with Gay-Lussac, what ends up happening with this one is if I lock the volume, if I heat this, the pressure is going to go up, right? 30, I'm going to stop at 50. No, I'm not. Here, I'm going to add more. And you can see how much faster they're moving, right? It's like a pressure cooker. Or if you squeeze your hands really tight, you're going to increase the temperature inside your hands right now. Like if you squeeze this really high, right, and you shook someone else's hand, your hand's going to feel really warm. Same thing. Or a pressure cooker or a rice cooker or an engine. That's all the connection with that. And again, pressure is hits, right? The more those molecules are hitting, the more the pressure is, right? The reason we feel increases and decreases in pressure is because it's messing with our natural equilibrium. When you have a really, really hot day and there's a high humidity, well, yeah, the pressure is going to feel more because there is more on you. It's that simple. And your body gets worn down easier because you're not used to it. It's like me throwing a weight vest on you and you're not ready for it. Same thing. And that conceptually is really kind of everything that's going on. With gases, right? The size of the container matters. Adding or lowering energy, which is going to slow them down. You guys can see it's getting slower. It's not hot and cold. Slow versus I'm waiting for this to get to about maybe 800. Maybe higher. I want you to really see that like it's speed. You guys can see I can get it to pop from this. Right? And it's also going to be about that pressure. How much are they hitting? Right? Those are the three variables with gases. And that's kind of really what it comes down to with that. I'm going to actually take a look at the final with gases just to make sure that that's specifically what it's talking about. Because there's one question that I'm remembering. Yeah, perfect. Okay, we're good. Yeah, we're good. And that's really what it comes down to. Okay, so far? And again, my students, you played with this for like some time, right? You figured out the equations. Okay. Now, admittedly, do you need the math equations to solve the final exam questions? No, you don't. Same thing that we did on the Unit 1 test. You don't need the math problems to figure it out. You can figure it out I mean, let's look at another example. Okay, I'm going to do a timestamp for this actually. Gas law, quote, math. Okay. And we're going to go 20. You probably noticed that I was able to get pretty darn close to some numbers, and I obviously wasn't doing any math. Okay. So here's how I'm doing it, right? Pressure and volume are inversely related. Okay. They're opposites. If I shrink it to 5, this number goes up. Watch. If I make it bigger, that pressure number is going to drop. Correct. That's an inverse relationship. Inverse, let me add that in, versus direct. And then it's a direct relationship if they're both going up or down together. So again, Boyle's law, or pressure and volume, is like this, right? It's inversed. But the other two, Charles and Gay-Lussac, are all direct. And I could prove that to you because if I heat this, temperature is going up and the pressure is going up. I could prove that to you right there. And if I shrink it, the temperature is also going down. So there's your also direct relationship. Okay. But again, I digress. So how am I able to figure all this out so fast? Well, that's actually what I just said with those relationships. If I cut this in half, I'm doubling the pressure because it's inversely related. So if I'm going halvesies with one, I'm going doublesies with the other, to make a joke of it. So yeah, this is going to be roughly just under 12. Close enough, right? If I had another pump, because this is one pump of gas, if I had another pump, it's going to go to about 23. If I double the temperature, I'm going to double the pressure. So this is going to be like 48-ish if I go to 600. It's going to be like 48-ish if I go to 600. And I'm going to get it right on 600 for you guys. Come on, come on. Oh, I'm going to get to 600. No. Close, right? I was pretty close. Pretty close. If I double this to 10, it's going to go, if I make it the box bigger, the pressure should go in half. So yeah, this would be like 23. So I'm using all those tricks about the direct and inverse relationships. I'm using those tricks to do all the math so quickly in my head. And again, my students, you did some of those calculations, right? Like if you remember that, you had to like solve it, do the graph, and then you got some of the equations. You guys actually did pretty good on those math problems. I didn't give you the equations yet. That's second semester, okay? But you can figure it out. You know, if the temperature goes up, the balloon gets bigger. The numbers are going up together. If I cool down the balloon, the numbers are going to go down together. So that's the relationship. So let me show you what that is, if that helps. Any questions with this before I get out of it? And then I'll type up what I was saying so you guys can visually see it as well. Does anyone want me to do anything or play with this at all? I'm going to drop the link in case you want to play with it. Let me do that. And any questions? Are we good? Okay. So gases, okay, 138. exactly. Okay. We've got volume. Oh, come on. That's the size of the container, pressure, particles hitting. We got temp, fast versus slow. This is liters. This is ATM or KPA, which I know it's been a while since you've seen this. I don't blame you. This is going to be Kelvin, Celsius. Sometimes you'll see Celsius. Kelvin's better. Kelvin's better. And then, yeah, really, oils is, again, going to be inverse. So it can be P1V1 equals P2V2. That's actually the math equation. If it's inverse, you're going to multiply, solve for X. So that's actually not too bad. Charles? And Gay Lusak are direct. And then Charles is V1, V2, and then it's going to be V1 divided by T1, V2 divided by T2. That's just cross multiplying. And then to be real with you, Gay-Lussac is the same, except this is pressures. And then you just cross multiply that one as well. Again, not as big of a thing. I just want to show you this is how the math works. Do you need these on the final? No. If you would like them, my students, I'll give it to you. I think some of you, I think, asked for the little math sheet, and I said figure it out. I'll do that again. I have no problem. I have them. But that's the whole direct and indirect, because I know some of you in math might not have talked about that yet, or it's been a while. Because I know they do this in algebra, but for some of you, that was 8th grade. So I don't blame you if you're like, what is this? But if it's inverse or opposite, it's going to be kind of like a multiplying situation. And if it's direct and they go up or down together, it's going to be division. So just so you see the equations, you will have to do the second semester anyway. So when Mr. Nenya, me, or Mr. Soroka goes over this, you could be like, okay, I've seen that before. And that's kind of really what it comes down to. Yeah, let me just direct is going to be an inverse is opposite. Yeah. And I think that answers the gas stuff. I mean, yeah, the big one is, the big one, just to, just talk about really quick. The big one's this. Like it's that really. Like temperature's not hot and cold. But Evelyn, because you asked the question originally, is that okay? Cool. And again, I should mention, like, gases are far apart. They move really fast, randomly. I'm pretty sure you all, like, just to say it. Just to say it. Like, gas particles are far apart. They go really fast. They have a low IMF. I mean, just to say it. Because with my students, you probably don't remember me saying this. I did say this a few times. I said, don't worry about it right now, but for what it's worth. Yeah. Is everybody, any questions on gases? I think we might be okay then. So we just discussed gases. Doo, doo, doo. Still spicy. Atomic theory. Yes. Atomic theory will be purple. Excellent. 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 Okay, we got 137, 10. All right. Okay, we got proton. We got neutron. We got electron. Okay, we have mass. We have charge. We have location. Ta-da! Yay! I mean, that's kind of the basic foundations of atomic theory. It's, the atoms are little building blocks that make up everything. You know what I mean? And the mass is 1 and 1 for a proton and neutron. Again, electrons do not have a mass. They are way too small. As a reference, just to kind of talk about it again, if this is a proton, okay, my stopwatch I've been using for the timestamps. If this is a proton, if I made one tiny little dot on here with my pen, or if I had a Sharpie, right? Let's say I had a silver Sharpie. If I made one little dot, that would be like 1,000 electrons. Like, not one, 1,000. So if this is one proton in size, a dot would be 1,000 electrons. Electrons are crazy small. That's why they don't have a mass. So do not count electron numbers in the total for the mass. That's not good. And in the same way, neutrons are neutral. Neutrons do take up space. They do have a mass, but they do not contribute for the charge. Those are the protons and electrons, which we talked about with charges earlier. Actually, one of the first things we talked about during the session. So How is this used? Long story short, okay, all of this is used like this. 3 keywords. Okay, atom, stable, protons equal the electrons. Okay, normal, stable, everything is good. 5 protons, 5 electrons. 7, 7, 10, 10, 12, 12, 80, 80, 73, 73. No charge. Okay, charge is 0. Okay. Ions, charged. Okay. The electrons are gained or lost. Okay. And we talked about if electrons are gained, that's like -1, -2. If they are lost, it's +1 or +2. Just so everybody remembers kind of earlier when we talked about that, it's this. No different. It's exactly like this. So all of these are ions with the charge. We're trying to become stable. No difference. Again, noble gases win. Charge is 0. No difference. And then the last word is isotope. Oop, come on. Oh, no. Sorry, it froze for me for a second. I have no clue what it looked like for your screen, so I apologize if that was weird. Okay. And then I'm just going to shrink this down to maybe 24. Perfect. And then the last word is isotope. An isotope is when the neutrons change. And again, it's going to go up and down. So the mass goes up and down. If you gain neutrons, you go up. You lose neutrons, you go down. So the way I like thinking about it is, and again, I showed you guys photos of me from when I was younger and older, right? In high school, I weighed a lot less than I do now. Out of college, I weighed more than I do now. 2 years ago, I weighed more than I do now. And it's still me. It's still me. Nothing's changed. I'm the same element, but the mass can change. So you can think about it like eating or working out. And it kind of all works like that. But again, it's really it comes down to this, which means, okay. And I'm literally gonna do a timestamp for this. And I'm literally gonna do this to you. Because it's incredibly important. Okay. Ions are electron stuff. Isotopes are neutron stuff. And some of you probably can figure out what I'm about to do, but I'm going to do it anyway, and you can't stop me. So there, I do what I want. Guess what? Guess what? Tell me in the chat what do you think I'm about to say. Get out of here with that. I'm going to kick you out. No. I'm going to wait until I see 6 people say it. I see 2. Keep them coming. I see 4, 5, 6. Okay, cool. There you go. If you change the protons. Andrew, get out of here with that. Also, hello. Good to see you. No, protons don't change. If you change the protons, my dude, you are cooked. You can't. You can't. Because you see, it's locked in. It's locked in. Right? The protons are the number. If you change the protons, you change the number, you're a different element. If I'm asking about copper and you talk about zinc, you're wrong. Straight up. You know? If I ask you to go to the store and buy me like some apples and you come back with plums, no. That's not how that works, right? That's not how that works. Which again is a thing. And again, where is this coming from? Right? Where is this coming from? Well, it's coming from this idea, right? That there we go. You got atomic number. That's literally protons. That's it. You got atomic mass, which is protons plus neutrons. Again, that's literally because they're the only things that weigh anything. I mean, let's look. Like, it makes sense that that's the formula, right? We can't add electrons because 0. 1,000 tiny things is 0. Like, it doesn't matter. And then the charge, right, is essentially you're comparing your number of protons versus your number of electrons. More protons positive, more electrons negative. Same 0. And that's really what it comes down to, you know? And that's everything, Danielle. That's atomic theory. Does that help? Does that answer the question? That's where like the chart is on the study guide where you have to like fill in all the different spots. That's where that comes in. I'm going to pull up the so I can tell you what page. Because I think it's page 3. Yep, it's page 3. That whole table on page 3 where you're filling all that stuff out, that's where it comes from. Yeah. And that's really it. And then again, like the protons and atomic number, right? If you have this, you know, just being straight up with you, if you have this, that means you know the element and the symbol. So that's pretty dope. Not to mention that proton is in both of these. I think we can agree that protons are the most important thing. So don't change them. Like I said, if you change the protons, you change everything. Don't do that. And that's atomic theory. What else we got? Because again, hey, I mean, we're over halfway done, y'all. Like, look at that. We're way over 40 questions, so we're way over halfway done. Oh yeah, for sure. And that should, pardon me, before we did that. So the charges work. It's exactly like this. Where'd it go? Perfect. It's literally this. It's literally this. So for example, here. Let's go. Might have froze. It did freeze. So let's say we have let's do 3 examples. Let's do okay, let's do vanadium +3, sulfur -2, and gallium. Okay. It's my computer's being very laggy, so please forgive me. I hope that doesn't look too bad for you guys. Sorry. Okay, let's talk about it. So when we're doing the charges, this is plus, this is minus, this is 0, right? There's nothing there. So for example, protons, vanadium is element 23. Sulfur is element 16. Gallium is 31. Okay, so we're good there. Again, I just looked it up on the periodic table. Protons are the element number. It is the symbol. So number 23, number 16, number 31. Nothing crazy there. Done. With the electrons, it's flipped. So the electrons here is 20. The electrons here is 18. And because there is no charge, the electrons are 31. So ion, ion, atom. Ta-da! And again, if you look, like 18 is a noble gas. Like this number checks out. This is argon. So, I mean, 18 checks out. I hope you can see the 18. The vanadium is a transition metal. It's a weird one, so don't worry about that. But that is how you do it. Does that answer the question? Cool. And again, that is on page 3 of the study guide on the table that you had to fill out, where they gave you some information. You have to fill in the rest. Mr. Nenny students and Sophia, I know you probably have that on your study guide too, where it asks you like proton, neutron, electrons, and you have to like fill in the rest of the info, just like the unit 2 test. Same thing. And again, another example on what we talked about with um with the charges coming back, right? Like that is such a big topic. We've been talking about that for months. Yeah, and it's page 3 of the study guide. Or if you look at the half sheets, it's page 3. And then there's some more on there. Definitely useful. I mean, not bad. I mean, we got a lot of good stuff done. I could definitely stick around for a little bit longer as well. I know it's already been for most of you over almost 2 hours. Is there anything else? It's up to you. I can keep going. We could do all this Wednesday night. Evelyn and Sophia, I don't know when your final is. The last one, IMFs. Andrew, just to make sure. Yeah, that's coming up for our second semester. So yeah, don't worry about that yet. All it is though, just to let you know. But yeah, it's not on our final. It's literally, is it close together or far apart? So it's literally like, are you close or far? That's all it is, but we're going to worry about that during solutions, probably March. So you good. I appreciate you looking at that though, because that's a big topic. But yeah, don't worry about that. It's not on our final. This is close to what yours looks like though, ish. Anything else? Oh, yes. Yes. Properties. Where'd it go? Oh, there it is. Okay. Evelyn, if you remember this, do you see the charges? And I'm going to wait for you to respond. Those charges are what allow electricity to flow. So here, there's an actual charge. Like sodium is +1, chlorine is -1. This allows electricity to flow through the salt water because this is salt. Just to be real, this is salt water. Because of these charges, it will conduct. In covalent, do you see those charges? So you don't conduct. You need those charges to conduct. This is what is called an electrolyte. So this is where Gatorade comes in and Powerade and all those like new products for like hydration and stuff. This is literally why they add salt to it and stuff. Salt is a cheap way to do charges. And that's why it conducts. It's also why it dissolves. It's also why it dissolves. Yep. That's another reason why I wanted to show this. Because yeah, this literally is what allows the electricity to flow. If you don't have a plus or a minus, right, it's not gonna do it. And then if you look at like these aren't good. They're close. They're close, but they're not these. These are actual pluses and minuses. These are kind of like wannabes. Actually, you know what? Here, let me draw this. Let me draw this. Let me draw this. Let me draw this. Let's go blue. So what this is going to look like, right? If you had like some stuff, Ionic is literally going to be plus and minus. Nonpolar is literally going to like vibe out like that. And polar covalent, because it's got a little positive and a little negative, is going to have a little bit of both. So it's going to kind of look like these. I don't know if that helps anybody. I know it's helped a few of my students. So I thought I'd maybe just write that really quick. And my students, you should recognize this if that helps you at all. You're welcome. I think I got too much stuff going on with these photos. That's okay. I'll make a separate thing. Oh, no problem, Evelyn. Cool. Yeah, because like the partial charges are kind of like, it's kind of positive. It's kind of negative. It's not straight up a positive and negative. It's close, but not there yet. It's trying. It's trying to do it, but not quite. I want to go out and do tug of war. It's just the weather just doesn't work when we teach this anymore. Like it used to be like always nice out when we used to teach this. Now it's like all over the place because it's like more in the fall. So like in my first 2 years, we went outside and did it, which is all good. Anything else? And anybody else? I know that was a lot of info. It's all on the computer. Oh, and Andrew, for yours, Andrew, this is different. You're actually the only student here who has a different final. So, and one, I appreciate you being here. The biggest thing, Andrew, for your final is the charge thing. If you know the charges, it's going to help you with ionic and covalent bonding, the Lewis structures, octet rule, valence electrons, and a bunch of the atomic stuff. So if you know negative is gaining and like +3 means lose 3, Andrew, if you understand that, it's going to help you so much. That's the biggest thing. That's the biggest thing. Oh, and Christian, yes, the math questions are on the. Sorry, I should say this. Christian, the math problems are also on the. This is new. The math questions are also in the multiple choice. Wait, can you guys see green? Can you guys see me do this? Wait, can you see the green? Wait, this is new. I didn't know I could do this. Can you guys see green? And then it like disappears, right? Oh, I didn't know I could do this. Look at that. Okay, I learned something. Cool. I didn't know you could do this. Well, it's disappearing really quick. Jeez. This is good for a quick, like, circle, though. Good. Okay, that's good to know. Cool. But yeah, that's the biggest thing. Anything else? And I'm going to save this so we could totally finish. We can ease. Oh, my word. We can finish the rest. You guys hit the big topics. I'm guessing you guys want more math review on Wednesday, though, because we only went over one of the math questions. Anything else before I stop the video? I just want to double check. So it seems like we're good. I just want to make sure. Okay, I just stopped presenting. So it's not recording anymore. It's going to take a little bit it took about 40 minutes for the video to process into my Google Drive before I put it to YouTube. YouTube, it uploaded in like 5 minutes, so it was really cool. So probably give it about an hour, let's say, before it's up. I will YouTube link to the Google Classroom and my YouTube channel. You don't need to subscribe to my YouTube channel to find it, but I will link it. So you don't need to go find it right now. I will link it. It'll have all the timestamps. That was really good, though. I mean, yeah, these, if we talk a little bit more about the math on Wednesday or in class, if anybody wanted to ask me while you're finishing the take-home test, like, you guys will be good. That was good. That was really good. Easily over halfway through the final. Easily. Is there anything else for the good of the group? Because again, I appreciate your time. I'm not trying to like keep you guys up though either. And I have to do my homework assignment. I'm only about a third through it, but I'm good. Anything else? Are people still there? Yeah, we chilling? I think we're okay. Yeah, I mean, yeah, you guys are good then. If anyone wanted to stick around or ask me like just like an individual question, that's totally fine. But yeah, if you're good, you're more than welcome to leave. It's once I get off this call, it'll generate the list for the extra credit, so I will know all of you are in here. Yeah, you could totally ask, or Thursday or Tuesday. Ask whenever you want. Yeah, I mean it's good things. And again, share the link. Share the link. I know the finals are probably a little bit, different with Soroka and Nenya, but I'm sure we're close. They're close. They're always close. Danielle, as you should. I want you to ask questions every day. That's what I want. I want you all to ask me questions every day. Goat. Emmanuel, when's the next home meet for wrestling? I'm bored. I don't want to look. Well, I'm lazy. I don't want to look it up. Because you guys have been away for a little bit. Wait, there's no more home ones? Really? That's crazy. What? Just West and that's it? That's crazy. Let me look. That was so much fun at the West. Oh, my word. Wrong East Aurora. I'm in New York. Let me get out of here. There we go. There we go. Aha, South Elgin. The 8th. Okay, cool. And then Elgin and Glenbard South. So yeah, you got 3 more. Okay, good. I'll try to make it to some of those. Oh, I forgot you did. Yeah, I forgot that you do wrestling. My bad. Sorry, I forget. No, he didn't get wrecked by you. You both are wrecking other people. That's how it is. It's not true. Don't. You're good. You're good. You're good. Yeah. But yeah, please, like if yeah, don't feel like you need to stay. Like if you're good, I think we're just messing around now. But I'm not gonna leave until everyone's off. Just in case. I'll have a good one. Oh, and Danielle, too, check out the timestamps. You got through a lot of them, but I know you missed the big ionic covalent thing. So, oh, you're in a different class, Andrew. That's why. This is all honors except you. Yeah, yeah. Denise, just get a pass for me, and I'll bring food up. But no, Andrew, I'm super appreciative that you're here because a lot of all of that we went over is on the final. So there wasn't a single topic that like you didn't need. So it was wonderful. I'm so happy you came. Normally, students in that class don't come to the review, so I'm super happy you came. Thank you. Oh, no problem, Evelyn. Yeah, we're doing it again on Wednesday. If you have any, because I don't know if you're red or black, I'm forgetting. I'm sorry. Um, yeah, when is your final? Are you red or black? You're red, aren't you? Yeah, are you red 1-2 or 3-4? No, or 7-8? Yeah, you're 1-2. Yeah, Evelyn, if you have any questions, because I know we missed density and we missed some of the states of matter, please, if there's anything on that study guide that we didn't go over, ask. Okay, shoot me an email, ask at practice. I can stick around and help. And they might cancel our meetings. Oh, Andrew, I got you. I thank you for coming. Thank you for coming. Yes, tomorrow's a work day. Tomorrow's a work day with the study guide. I'm going to go over like the logistics of your final, so I'm going to tell you those numbers as well. Um, Admittedly, it got finished really late on Friday, so I still have to look at it a little bit more because I was ready for that shorter final, and then they added the questions back. So, as you can imagine, I'm not pleased about that. I don't think the final should be 76 questions. I think we were really good with the 40. It was like these are important. Like it wasn't any extra fluff. It was like these are the good questions. So I will we'll definitely have some time. I know it is. And I'm not happy about it. So I'm taking care of you guys. It's not right. So you will get a lot of information, especially with Unit 2. Like Unit 2 was our fault. Unit 2 wasn't your fault. Unit 2 was our fault. I'm going to make sure you guys are 100% good on that. But yeah. Yeah. Later, everyone. Thanks so much for coming.